Friends, welcome to the 14th lecture titled Response Spectrum. It is a very important lecture where we try to discuss certain important terminologies which we will be using later in case of analysis of offshore platforms or offshore structures under special loads. So, in the last lecture we said that ice loads can be expressed as ice spectrum. It depends on couple of parameters. One of them influences the response or the ice force computation very significantly, the other one does not. We also said that ice acts as breaking ice cones on the platform. Broken ice pieces are cleared up, but these ice forces acts, therefore, ice forces act as periodic loading and sets or and causes ice induced vibrations. Ice forces on narrow conical structures are actually composed of similar ice forces or I should say ice force pulses of varying random parameters. Therefore, ice force which is expressed as f of t is given by f of t is actually equal to summation of various pulses of t minus t I. In this case, n is what we call length of loading function, and T10 is 0, whereas T10 is actually equal to j to 1, I to 1, jj, or I should say Tj for I greater than 1. The force F I of t in the equation is ice force model for any specific event of ice. Or I should say specific event of ice failure. So, that failure can be defined as 6 f 0 I t by T I for t ranging between 0 and T I by 6. Otherwise, it is equal to 2 f naught I minus 6 f naught I by T I for t ranging between T I by 6 with T I by 3. Otherwise, it is 0 for any value of t between T I. In the above equation, f 0 I for I equals 1, 2 etcetera denotes actually the random ice force amplitudes and T I denotes the random ice force periods. Various researchers showed that experimental investigations conducted on the random ice forces or let us say ice forces show varying amplitudes for random ice periods, but they have a weak correlation. That is the interesting news. Therefore, variance of ice force is given by d f of t, which is expected value of f square of t minus square of expected values of f of t, where we know that E of anything is expected operator. Also, E square of f of t is actually f 0 square by 36, and hence E f square of t is f 0 square by 9 plus sigma f 0 square by 9, where f 0 and sigma f 0 square are actually the mean and the variance of force amplitude f 0. Therefore, d of f of t, which is the variance of the ice force, is actually f 0 square by 12 plus sigma f 0 square by 9. It is also said that the standard deviation of ice force amplitude is about 0.4 times of that of the mean ice force amplitude. You can see this from Q et al. 2006. Therefore, the 0th moment, which is actually d f of t, is approximately 0.1 time of f bar square. So, friends, we have been discussing the input loading to offshore platforms, be it waves, be it wind, be it current, be it ice loads. We will also further discuss earthquake loads, extremely high sea wave loads, etc. in the coming lectures. All these are discussed as in the form of input spectrum. So, we have force spectrum, which is considered as an input for the analysis. We have also discussed something about the response spectrum. So, interestingly, if you know the force spectrum of a given system, you can always find the response spectrum of the system which is interacting with these loads by connecting the force spectrum to the response spectrum. So, we will discuss that in this lecture in detail. Before looking into that, let us ask series of fundamental questions to understand certain clarity. Let us first ask, what is an ergodic process? Ergodic process is actually a stochastic process if its statistical properties like mean and standard deviation can be deduced from a single sufficiently long sample of the process. So, the whole convenience is to identify that single long sample of the entire process whose mean and standard deviation will be used in computing the whole analysis. This means that ergodic actually refers to any sample from the process which represents the average statistical properties of the entire process. The second question which comes in mind is, what are the advantages or what is a salient advantage of having or let us say identifying an ergodic process? Interestingly, regardless of any process you choose, one selects for the analysis, it does not matter what process you are selecting, if it represents the whole process, it is very advantageous. That is, a single process chosen as a representative of the complete process actually and truly represents the complete process, not the section of the process. That is interesting. Let us define ergodicity mathematically. So, that is the third question, how to define ergodicity mathematically. Let us say constant mean of any process is mu x, which is nothing but expected value of the variable. Autocovariance of the process is given by this equation, which is nothing but the expected value of x of t minus mu of x into x of t plus tau minus mu of x. In fact, I should use a different symbol here. I should say this one, mu of x. So, that is let us see equation 1 and equation 2. So, equation 2 implies that the autocovariance, which implies that the autocovariance depends on the lag tau, because there is a lag tau, and does not depend on time t. See here, autocovariance depends on the lag tau, does not depend on time t. Hence, statistical properties like mu x and gamma x of tau are ensemble averages and not time averages. That is very interesting statement, which you want to define the ergodicity mathematically. The process is said to be mean ergodic if the time average estimates converges to the ensemble average values, that is mu hat of x is 1 by t of 0 to t of x of t dt, which actually converges to the time average converges to mu x at t tends to infinity. Similarly, the process is said to be autocovariance ergodic if the time average estimates converges to ensemble average estimates. Mathematically, R x of tau hat is time average 0 to t, which is x of t plus tau minus mu x multiplied by x of t minus mu x dt, which converges to gamma tau as t approaches infinity. What is a classical example of an ergodic process? So, that is the fourth question which one is interested to know. For example, friends, the stationary Gaussian process are generally seen as example of ergodic process. Suppose I want to know ergodicity in case of discrete random process, then how do you define ergodicity? A discrete random process let us say, to be very specific, a discrete time random process x of n is ergodic if the mean converges to the ensemble average that is mu hat, which is now 1 by n of n equals 1 to n x of n, which now converges to expected value of x as n tends to infinity. So, friends, we have understood that the input forces defined in terms of spectrum has certain parameters based on which the values are estimated. To estimate these spectrum, we need parameters correlation characteristics. We generally assume this to be ergodic and stationary process. Now, we understood what is ergodicity, and now we look further into what do we mean by response spectrum and how do we actually bridge the response spectrum to the input force spectrum to actually get the response. We now agree that in many cases offshore platforms are actually exposed to environmental loads which can be modeled as piecewise stationary process. Just for recollection, what is a stationary process? Stationary process is that process for which statistical properties like mean value and standard deviation, these are only examples, there can be many, are same at all points in time or in position. We explained this earlier as well, just to recollect this idea. Therefore, mx is nothing but expected value of x of t, which is now a constant. That is, mx is also mx of t, which is satisfied. That stationarity. Okay. For a stationary process, autocorrelation function, which is R x of tau, can be defined as expected value of x of t plus tau. Please understand, the autocorrelation function is only a function of tau. We need to check this. Check this statement, that is, m hat of x of t, we know that it is going to be average of j equals 1 to n of x j of t, and r hat of x of t comma t plus tau is actually 1 by n of summation of j equals 1 to n x j of t x j of t plus tau are independent of time. That is what we need to check. If they remain independent, of time, then the process is stationary. Alternatively, mx, which is expected value of x of t, is also said to be constant, and autocovariance function C x of tau can be said simply as E of x of t minus mx x of t plus tau minus mx, which is function of tau only. One can now ask me a question, what is the essential advantage of considering the loading or the process as a stationary process? That is a good question. Let us try to answer this. Friends, for a stationary process, we have got a very serious advantage. Let us highlight this and understand this. For a stationary process, transfer between the load and the response which we are interested in can be modeled as linear time invariant system. That is a very, very interesting statement, and it is one of the very serious advantage we have. The system then can be characterized by a transfer function. So, transfer function is the one which is going to bridge the response to the load in a stationary process. Therefore, relationship between variance spectrum of the response, which we call as response spectrum, and variance spectrum of the load, which we call as load spectrum, is determined by a transfer function So, our job is now to understand this transfer function. So, let f of t denotes a stochastic load process. Assume that f of t acts as a linear time invariant system acts on, actually not as, acts on a linear time invariant system whose impulse response function is given by h f x of t. What does it mean? It means that for each realization f of t of the sample capital F of t, there exists a corresponding x of t of the total response set x of t. So, one to one link, one to one bridge, one to one correspondence will be there. Hence, x of t is minus to plus infinity h f x as s f of t minus s ds. Let us say 1a, which can be said as 0 to infinity h f x s f of t minus s ds, because h f x s is 0 for any value less than 0. We are looking for only positive realization. Therefore, equation 1 clearly establishes a relationship between realization of the load process and the corresponding response process. This connectivity or this connection can be described mathematically as x of t is 0 to infinity h f x s f of t minus s ds. Equation 2 interprets that relationship between all corresponding pairs of realization between f of t and x of t exist. There is a very important ideology here. Impulse response function or the transfer function which determines the connectivity between the load process and the response process is completely defined by the properties of the system only. That is, transfer function is independent of any given load. It is dependent only on the properties of the system. So, that is a very interesting and strong statement we have, which is very helpful in interpreting this transfer function, which actually connects the input process, which is the load spectrum, to the output process, which is in my case the response spectrum. Let us try to understand one important terminology, h f x t. Let us try to understand this term. Here the index f x is actually the indicator which connects f and x. Let us say for example, y of t is the response and g of t is the load process, just for understanding. Then the transfer function or the impulse response function can be indicated as, please understand, indicated as, not defined, h of g y of t, which is as identical as h of f x of t. So, this is actually an indicator. Okay. It actually connects the force and the response. If the force is g and the response is y, then I write the impulse response function in this terminology. So, it is actually an indicator for the whole analysis. Now, let us try to extend the discussion for identifying the mean value of the response please understand we are now looking for the mean value of the response process. So, let us say assume that f 1 of t, f 2 of t with respect to f n of t is the sequence of realization of the load process f of t. Similarly, x 1 of t, x 2 of t till x n of t denotes the corresponding, okay, that is very important, the corresponding sequence of realization of x of t. Then 1 by n of summation of j equals 1 to n x j of t can be said as 1 by n of summation of j equals 1 to n of integral of h f x s. Now, we understand this indicator f j t minus s ds, equation 3, which can be extended as, okay, this integral is from 0 to infinity. So, rewritten as 0 to infinity h f x s, that is the integral value, and I can simply say summation of j equals 1 to n of f j t minus s ds. Equation 4 leads to a very interesting understanding. So, this leads to expected value of the set of response processes is actually limit n tends to infinity 1 by n of summation of j equals 1 to n of all the corresponding Rayleigh's set subset of x of t, which can now be expressed as integral of 0 to infinity of h f x s indicator impulse response function. Then I implement this limit n tends to infinity 1 by n of summation of j equals 1 to n of f j t minus s ds, equation 5. Look at this carefully, I can rewrite this as 0 to infinity h f x s expected value of f of t minus s, because it is t minus s over the summation limit, which is actually expected value by definition. So, equation 6. If f of t, the complete set of the load process, is a stationary process, then we agree that mf is actually equal to expected value of f of t, which is a constant. We already said that in the beginning. Hence, expected value of x of t, which is going to be mf of 0 to infinity h f x s ds. So, equation 7. From equation 7, looking at the right hand side of equation, let us say right hand side of equation 7 is interestingly independent of time. That is, which tells me is that mx, which is E x of t, is constant. That is a very important assumption and characteristic of a stationary process, which is also ergodic. Let capital H f x omega be the transfer function that corresponds to the impulse response function of H f x t. In that case, H f x 0 is 0 to infinity H f x s ds. Now, equation 7 can be also rewritten as expected value of x of t is mf, because 0 to infinity ds is actually equal to h f x 0, which is again mx, because E x of t is mx. It means mx is actually f x 0 of mf. From the fundamentals of dynamics on single degree freedom system model of a spring mass system, let us say of a spring mass system, spring mass damper system of a single degree freedom model, which I would request you to refer back to NPTEL notes on dynamics of offshore structures, lectures given by me. I borrow the derivation from there directly. I am not going to derive the derivation now in this lecture. So, we know that for a steady state response, dynamic amplification factor which DAF, which is indicated as D, is given by 1 by root of 1 minus beta square plus 2 zeta beta square, where beta is the frequency ratio and zeta is the damping ratio. For a weakly dampened system, it is also known that the dynamic amplification factor maximum will be approximately 1 by 2 zeta. So, just for understanding, if zeta is just 2%, you will see D max is about 25 times, which implies that even for small oscillations, excited by forces may lead to large responses. Hence, it is advisable to relook the transfer function in this perspective. So, friends, in this lecture we discussed about the ergodic process, the stationary process, some extension of I spectrum. We are in the process of connecting the force to response using impulse response function, but I call this as a transfer function which is independent of time and load, but depends on system characteristics. We will extend this discussion in the next lecture and try to revisit the transfer function with more detail, because the dynamic amplification is phenomenally high even for small oscillations when the system is weakly damped. We are looking for a compliant structure which is essentially weakly damped with large bandwidth of frequencies, and we want to know what would be the characteristic of the response spectrum under these situations. Thank you very much.